Hey everybody. So, dealing with our systems of equations, we're now going to get into the second method of solving these systems, breaking away from the graphing. Now we're going to solve them a little more what's called algebraically by using this method called substitution. Learning objective for the day, I can solve systems of equations using substitution. Solving systems of equations. We could solve using these different methods. The idea is to determine which method is easiest for that particular problem. These notes show you how to solve a system algebraically using substitution. So, step number one, solving substitution. Solve an equation for one variable. We need to get one variable all by itself. Pick the easier equation. The goal is to get either y equals, x equals, a equals, b equals, whatever it is, any one of those variables we want alone on one side of the equal sign. Whichever one's easier, that's the one we're going to pick. Step two, substitute. That whole y equals or x equals or a equals, whatever that variable equals, we're going to take all of that and plug it into the other equation. Step three, solve that new equation. So we've isolated a variable, taken what it equals, plugged it into the other equation. Now we have one equation with just one variable. Solve that equation. We know half the solution at that point because we know what one of those variables equals. So the fourth step, plug that value back in, find the value of the other variable. Then you'll have your x and y solved, and you'll have the solution to your system. But step five, check your solution. Taking that x and y that we just found, plugging it back into our original equations, making sure we get true for both of those. So there's our 5 steps, solving by substituting. Let's take a look at how it works. Here's example number 1. You have x plus y equals 5. You have y equals 3 plus x. Step number 1, get a variable all by itself. Now looking at these two equations, do we have a variable already isolated? Do we have a variable already alone? The answer is yes. That second equation is already solved for y. The y is already alone in that second equation. So we're going to take that part of the equation and plug it in for y in the first equation. So that whole y equals 3 plus x, the whole thing that y equals, we're going to take and plug it into the top equation for y. Looks like this. Instead of x plus y equals 5, we're going to take what y equals and plug it in. So now I have x plus 3 plus x, which equals 5. Step number 3, solve that equation. So I have x plus 3 plus x. Since I have x plus x there, that makes 2x. And now I can solve this two-step equation from here. Get rid of the plus 3 by subtracting. Get rid of the times 2 by dividing. I get x is equal to 1. Find the variable alone, plug it into the equation, solve that equation, we're halfway there. We've got one of the variables solved for our system. But remember, systems have 2 equations or more, and they have at least 2 variables. So we got to find that other variable. We're going to take that x equals 1. We're going to take that 1 and plug it back in. I'm going to pick the top equation instead of an x. I now have a 1 because I know x equals 1. I have 1 plus y is equal to 5. I get rid of that plus 1 by subtracting. 5 minus 1 is equal to 4. So now I have my ordered pair. I have my solution. X was 1, y was 4, so I have 1 comma 4 as my solution. Let's check it. Plugging it back into our equations, I get x plus y, that's 1 plus 4. That's 5, so that one's true. I get y equals 3 plus x, so 4 equals 3 plus 1. That's also true. Since I have 2 trues for my solution, I know this is the correct solution. Going through the steps, get a variable alone. Take what it equals, plug it in. Solve that equation. Take what that variable equals, plug it in. Solve for that other variable. We've got both answers with the x and the y. We could check it, and we're done. Comparing this back to the method we just did, we know our solution is 1 comma 4. What do you think the answer would be if you graphed the 2 equations? Do you think that answer would be different? Do you think that answer would be the same? Would these two lines be parallel lines? Be that coinciding lines where they're exactly the same? Or would they intersect right at that 1, 4? Hopefully you're thinking that they intersect right at that 1, 4, because whatever solution we find with this method, it should be the same solution we find with any other method. So if we graph these equations, we would have found that they hit each other right at that 1, 4. We would get the same solution no matter what method we use. It's just a matter of which one's easier. So let's move on. Here's example number 2. You have 3y plus x equals 7, 4x minus 2y equals 0. Solve an equation for one variable. Do we have one variable all by itself? Not this time. But there is a variable that's going to be easier to solve for. Notice we have a 3y, an invisible 1x, a 4x, and a negative 2y. Y, x, and the second y, they all have a coefficient that's not 1, which means if I'm solving this, I would have to divide by that coefficient to get the final answer and get that variable all by itself. This x value, I don't have to divide. So we're going to solve for this x because it's easier than all the other ones. Solve for that x by moving the 3y back to the other side. So I subtract that 3y. I get x equals negative 3y plus 7. So now let's go to step number 2 and substitute and plug that thing in. So x is equal to all of this here. Whenever you see an x in your equation, plug in what it equals. So I'm going to have 4 times this whole mess over there. Negative 3x plus 7. Now that I have it here, I've got to solve. So I have 4 times negative 3y, 4 times positive 7, then minus 2y is equal to 0. 4 times negative 3y is negative 12y. 4 times 7 is 28. So I have negative 12y plus 28 minus 2y is equal to 0. Combine your like terms here. I have negative 12y and a negative 2y. That makes me negative 14y. Get rid of this 28, get rid of our constant by doing the opposite, by subtracting it. 0 minus 28 gives me negative 28. Get rid of this multiplier by dividing. Divide that negative 14 on both sides. Negative 28 divided by negative 14 is positive 2. So I have my y is equal to positive 2. We're going to take that and we're going to plug it back in. You can plug it into any equation that you want. I'm going to pick the bottom one this time. We have 4x minus 2 times y, so 2 times 2 is equal to 0. 2 times 2 makes 4. Get rid of that minus 4 by adding. 0 plus 4 makes 4. Get rid of that times 4 by dividing. 4 divided by 4 makes 1. So my solution here is 1, 2. My x, y. 1, 2. Let's check that solution. Knowing that it's 1, 2, plugging it back in. I have my y here, so 2 gets plugged in. I have my x here, so x goes to 1. 3 times 2 is 6. 6 plus 1 is 7. That checks off. That's true. Do it again for the second equation. 4 times 1 minus 2 times 2. 4 times 1 is 4. 2 times 2 is 4. 4 minus 4 is 0. That also checks off. So we know our solution's good, that 1, 2. When do you think solving systems by substitution is easier to do than graphing? What I'm hoping we're thinking, guys, what I'm hoping we're realizing is that when we start having equations that aren't in slope-intercept form, that aren't very easy to graph, that we should use a different method. It's a lot of work to try to graph these things and then find where they intersect. If we see problems that are in slope-intercept form, why mess around? Just graph them, right? Because that's easy to graph. Intercept, slope, find where they intersect, done deal. But when you have something like this, and it's not in slope-intercept form, and it's not going to become slope-intercept form real easy, don't graph them. Use the substitution method. There's 2 examples. Let's see. If I have more, good, I do. Here's example number 3. X equals 3 minus y. X plus y is equal to 7. Step number 1, solve for a variable. If you notice, guys, I've got that x in the first equation all alone. So I don't have to solve for any of them. I'm just going to use that first one. I'm going to take that 3 minus y and plug it in for x in my other equation. So instead of x plus y equals 7, I now have 3 minus y plus y equals 7. Combining like terms here, I have a negative y plus y. Negative plus goes away. So now I'm left with 3 equals 7. Whoa, wait a minute. Does 3 equal 7? No, that's not true at all. This is called a special case. Just like how we had those special cases before. When we intersected on a graph, one solution, like we saw in example 1, example 2. When we had parallel lines, no solution. When we had the same line, infinitely many solutions. So this is one of those special cases. Since we ended up with 3 equals 7, and that's not true, this is a no solution. If we were to graph these equations, it would have ended up as 2 parallel lines, 2 lines that never intersect. This means they have no solutions at all. So now you've seen it with the graphing method. This is how you would find no solutions in a substitution method. Your variables eliminate, and you're left with 2 numbers that do not equal each other. Let's do one more. 2x plus y is equal to 4. 4x plus 2y is equal to 8. This one's a little trickier. Why? Because step 1, I don't have a variable all alone. But just like what we saw in example 2, this variable has no coefficient. It's just that invisible 1 coefficient. So let's solve for this one by getting rid of that 2x by subtracting it. So now I have positive y is equal to negative 2x plus 4. Let's use that, plug it in for the y in our second equation. So I have 2 times y, well, not anymore, because my y is equal to this. So we're going to have 2 times negative 2x plus 4. Let's distribute this thing and solve away, and that's step number 3. So I have 2 times negative 2, and I have 2 times positive 4. 2 times negative 2 makes negative 4. 2 times positive 4 makes positive 8. So now I've distributed. I can combine some like terms here. I've got x's, 4x minus 4x. Whoa, that goes away. Special case again, guys. But notice this time we have the same number on both sides of that equal sign. We have 8 equals 8. So since this is true and we have no more variables, the variables got eliminated. This is the infinitely many solutions special case. The majority of the time, guys, you're going to be substituting. You're going to have an actual solution, an x and a y, and then check it, make sure it works for both equations in your system. But it's important to be aware that even with different methods, you still have those different cases where you have no solutions or where you have infinitely many solutions. This is what it looks like in substitution. Your variables are eliminated. Your variables are gone. You're left with 2 numbers on either side of the equal sign. If they're the same, then it's true. Infinitely many solutions. If they're different, then it's false. No solutions. Alrighty, guys, let's work on those practice problems, and then let's see if we can figure out this solving by subbing. Thanks so much.